Hey everyone, welcome. On behalf of Forge College, I'm super excited to kick off this explainer. The title of today's video is exactly what we're going to do: optimization strategies for reducing Solana costs. Now, if you've been following our track from EVM to SVM, transitioning from Ethereum to Solana, you know we've been getting pretty deep into the mechanics. We just wrapped up comparing gas to compute units, right? Well, today, we are pulling out the technical pins, rolling out the engineering blueprints, and getting to work. We are going to drastically cut down your Solana transaction costs. So we're moving beyond theory and diving into some highly targeted, practical optimization strategies. Let's get into it.
Okay, so in our last lesson, measuring compute units and real transaction costs, we basically hooked up all our diagnostic tools to the pipes, just to see exactly where the pressure was dropping. Well, we've measured the compute. Now, how do we actually shrink it? It's time to stop just looking at the plumbing leaks and start fixing them. No more guessing. We're going to use hard data to streamline our code with targeted, measurable optimizations.
Here is our master schematic for today. First, the blueprint, then consolidating instructions, state serialization, rent and ordering, dialing in that compute budget, and finally, validating those savings.
All right, Section 1, the blueprint. Let's bridge that concrete measurement to practical optimization.
So when you actually sit down and look at your profiling data, you're almost always going to find your compute units draining in these 4 common hotspots. We're talking repeated program invocations, wildly expensive state serialization, redundant account reads, and, oh man, those sneaky on-the-fly rent operations. We're going to use the data from your previous profiling tests to target these exact issues in the checklist. Honestly, it's way better than just blindly whacking the engine with a wrench, right?
Moving right along to Section 2. Consolidating instructions.
This is where EVM developers can find some massive potential savings, and I absolutely love this analogy. Think of your Solana transaction like a freight train, okay? Every instruction is a train car. Now, coupling multiple cars together, that incurs a heavy cost. You've got handshakes, account lookups, permission checks, runtime environment setups, literally every single time you attach a new car. It gets super expensive. But if you pack multiple payloads into a single, consolidated, tightly packed car, you dramatically lower your overhead. You're carrying the exact same payload, but you're only paying that heavy coupling cost once.
So the real question is, how do we actually build this single train car in our code? Well, by modifying your client-side builder to use a single instruction that accepts a vector of subcommands, you completely eliminate the need to repeatedly enter and exit the on-chain program. So instead of calling, say, program X 3 separate times for 3 similar actions, you just call it once and say, hey, here's a list of 3 things I need you to do. The on-chain handler just iterates through them in sequence. It's actually a real game changer. So incredibly efficient.
Okay, Section 3. Smarter state serialization.
Inefficient deserialization is a lot like unpacking a massive, chaotic suitcase, just throwing clothes everywhere, all just to find your toothbrush. It's exhausting for you, and trust me, it's exhausting for the SVM too. To fix this, we need to replace those verbose, bloated encodings with tightly packed binary layouts. Like, if you're using something like Borscht, make sure your structs are tightly packed. Pack your booleans into bit fields. Oh, and here's a massive tip. Move rarely read fields out to a separate account entirely. Doing that drastically reduces the amount of data your program has to parse and validate on those critical, hot execution paths.
Next up, Section 4. Rent and instruction ordering. Let's look at the optimal order of operations for your instruction logic. First off, always perform your read-only checks. Just get those cheap validations out of the way before you start doing any heavy lifting. Second, cache your deserialized values locally. Seriously, if you need to read an account multiple times in a single instruction, do not fetch and deserialize it over and over again. Store it in a local variable. And finally, step 3, execute your expensive writes last. Reordering your logic to cache deserialized state prevents duplicate account reads, and it just keeps your whole program trace incredibly clean and compute-friendly.
Now let's talk about rent. On Solana, accounts need to maintain a minimum balance to be considered rent-exempt. I know, for EVM developers, this concept can be a little jarring at first. But think of pre-creating a rent-exempt account during your initialization flow, kind of like buying a house, instead of renting a hotel room every single night on the fly. When you allocate rent-exempt balances once and just reuse those accounts, you completely eliminate those nasty, unpredictable compute spikes that happen from account creation and on-the-fly rent checks during your critical transactions. So seriously, buy the house.
All right, Section 5. Tuning your compute budget.
Let's take explicit control of our resource limits.
The absolutely crucial point here is this. Never, ever rely on the default compute allowances on Solana. Just don't do it. Relying on defaults is blind, it's risky, and honestly, it can lead to unexpected failures or just overpaying for no reason. Instead, explicitly request only the exact compute units your optimized path actually needs, plus maybe a tiny safety margin based on that baseline testing you've already done. By setting explicit compute limits, you're making sure your execution is controlled, it's safe, and it's highly predictable.
Now, you might be wondering, what about priority fees? Well, if you're facing network congestion, you can totally add a compute budget instruction to set a modest priority fee. But remember, and this is key, this is a calculated, measured trade-off to ensure timely execution. It is not a mandatory reflex for every single transaction. Don't just blindly crank up the fee, okay? You've got to measure the marginal cost versus the actual benefit of getting your transaction included in that specific block.
Finally, Section 6, validating the savings. We need to run our before and after checks, which creates a pretty bulletproof 4-step workflow. Step 1, measure your baseline. Step 2, apply exactly one fix. Actually, let me emphasize that, just one fix at a time. Step 3, measure again. And Step 4, run your regression tests. This rigorous incremental loop isolates the exact impact of each individual change. Because think about it, if your tests fail, like maybe you accidentally broke the atomicity of a transaction by consolidating it, you'll catch it immediately, and you can roll back that single change instantly without having to untangle a massive mess of updates.
So what's the actual payoff here? Is it really worth all this effort? Absolutely. When applied correctly, these consolidation and serialization techniques can realistically shave a massive 10 to 30% off your total compute units. No way, right? But it's true. For high-throughput applications, we're talking about massive financial savings and significantly better network performance.
Let's do a quick recap of our engineering schematic today. Remember the analogies. Pack your train cars tightly by consolidating your calls. Organize that messy suitcase of yours by using compact serialization formats. Order your logic smartly to cache those read states. Definitely buy the house instead of renting by pre-creating rent-exempt accounts. And finally, always set a firm, explicit compute budget. Remember the golden rule. Measure first, apply one targeted change, and then validate.
And that pretty much brings us to the end of our blueprint. Your compute is now beautifully optimized, but the next challenge is making sure it actually stays that way as your codebase grows. So how will you automate this tracking in your CI/CD pipeline next? Well, that is a wrap for this Forge College Explainer. I highly encourage you to head over to forge.college to learn more about this subject, dive deeper into Web3, and just keep your freshly optimized scripts ready for our next lesson, where we'll tackle continuous automated cost tracking. Thanks so much for hanging out with me, and happy building.